Welcome back, ladies and gentlemen. In this video, we're looking at this idea of work. Now, you've heard the word before. We use this word all over the place in normal conversation. But to a physicist, this word means something very specific. So I want to remind you of something. Oh, by the way, I've got my buddy Genos here to help us out with the video. I want to remind you forces. There's three extremely important words that you're supposed to learn in this class, and that's that forces change motion. Okay, so forces change motion. They cause accelerations, right? They kind of change velocity. So right. The question though is, how much will the motion change when you apply a force? How much do forces change motion? We could look at that from a point of view of kinematics. So we could say, well, we got an initial velocity and a final velocity and an acceleration and a displacement and a time, and we've got equations and we can work things out. But there's actually a nicer way of doing that here, and you'll see that. Now, the amount of work, the amount of, how much the force changes the motion depends on two things for that force and that object. It depends on the size of the force, and it depends on how long that force acts. Now, when we say it that way, it's a little bit ambiguous. How long the force acts could mean time, how much time goes by while the force is acting on the object. It could also mean distance, and distance would be, well, how far does the object travel while that force is acting on it? And for our purposes here, distance is the one we need to use when we're talking about the work done. And actually, if we were dealing with time instead of distance, well, that would lead us down a different kind of topic. That would be momentum and impulse, and we'll get to that later. So we're going to deal with the distance the object moves while the force is acting on it and the size of the force. And so here we go. We have the basic relationship. The work done on an object. Well, that work, something is done to this object by the world around it, or by some force, essentially. And the work done that will change the motion is going to be equal to the force times a distance times the cosine of an angle in between the force and the distance. What does that mean right there? Well, essentially, and this is where Genos is going to come in and help me out. You have a force, and the force acts in a certain direction. Forces are vectors. And the object will travel a certain distance. And that distance, well, it's kind of the wrong word to use. Displacement would be a much better word. However, the equation typically is shown with a d for distance, although displacement works as well. Here's how Genos helps. So he's about to enter a battle with his enemy, and he's going to get ready. So he fires his built-in cyborg rocket engines, the jets, and he lifts off the ground to get ready for the battle. So there was a force acting on him, and that force was in the upward direction. Okay. And he also traveled a distance in the upward direction. So I want you to just pay attention to the directions of the force and the direction of the distance traveled. They're in the same direction. They basically overlap. And do you know what the angle is between two lines that overlap like this? Well, the angle is 0. Well, okay. So does that mean no work is done? Oh, no. What it means is, on your calculator, you have 0 as the angle, and you type the cosine, and the value is 1. So you're going to multiply force times distance times cosine of 0. And cosine of 0 equals 1 in this case. Now, the angle won't always be 0, and that's why we have to leave the cosine theta in the equation. But let me show you what that looks like. So let's say you have this box, and here's a surface. The box is resting on a surface, kind of like this. And you're going to apply a force to that box. And maybe the force, you're not pushing straight sideways. The force is kind of here. And now what's going to happen, though, is the box is going to slide to a new position. Okay, so how is the distance traveled from there to there? Okay, so you can see the distance itself has a direction to it. It was horizontal, but the force is kind of down at this angle. All right, how much work was done? Well, the work done depends on that force. Remember, it depends on the size of the force. It depends on the distance traveled, because we got that in the equation, and we're talking about distance. But it also depends on the angle between these two arrows. How do we measure that? Well, if I just sketch an arrow here for the distance traveled, And I'm going to sketch an arrow for the force. But what I'm going to do is I'm going to take the beginning point of each arrow and I'm going to overlap those beginning points. And so the force arrow will be here, like that. And so this is my distance arrow, and this is my force arrow. And you can see that they kind of match that and that and that. Now, it's easy to see the angle between them. The angle between them is right here. There's angle theta. Theta is that Greek symbol, looks like an O with a horizontal line through it. Okay, so we could do this now. We could calculate the work you did on this box by multiplying force times distance times the cosine of the angle. So the cosine of that angle between those two things. And that angle would have to be known, or you would have to measure it, right? Now, there's one more thing about this, and this is going to be an interesting little fact, probably also useful, because you multiply a force times the distance times cosine of an angle. Angle's measured in degrees here. And you get your work. So what are the units going to be? All right, so we have the equation's got an equal sign. On the left-hand side, we're going to have the units of work. Well, we don't know what they are yet. Let's see if we can figure it out. On the right side, we've got the units of force, which are newtons, and the units of distance, which is going to be meters. And now the angle is measured in degrees, but degrees is not exactly like a unit the way meters is. And you take the cosine of the angle and the units will disappear anyway. So there's no units with a cosine of an angle. You end up with just a number. So this is our units on the right hand side. At first, it doesn't seem terribly helpful. However, do you recall what a newton is equal to? How can we break this up? Well, remember the equation for force. Newton's second law says a force is equal to a mass times an acceleration. And so a mass is a kilogram, and an acceleration is a meter per second squared. So a newton breaks up into a kilogram meter per second squared, and we are multiplying by meters. And so this kind of, everything combines into meters times meters is meters squared. So I've got on the top kilograms times meters squared per second squared. Now, that should look a little familiar to you. That should look like the units of energy. And what are those units of energy? They're joules. Work is also measured in joules. That's really interesting about this. So, Joule is how you say that, joule, or joules if it's plural. Cool. And so you talk about how many joules of work were done. Or, if you're dealing with energy, how many joules of energy does an object have? All right. That's kind of curious that work and energy are both measured in joules. Does that mean they're connected or related somehow? Interesting. What about that connection? Remember that, well, forces change motion. Motion. Is there some kind of energy that's related to motion, the energy of motion? What's the name of that?